All right, and then this is all Dylan, so take it away, Dylan.
All right, let me get Google Meet to cooperate with me here. So, hi everybody. My name is Dylan Dickerson. I'm a software engineer at NCAR in the mesoscale and microscale meteorology lab we call M-Cubed. And I'm going to be giving an webinar about MPAS atmosphere. This is a model that I work with and I'm part of the development team. So MPAS stands for the Model for Prediction Across Scales. It's a collection of a few different cores and models that are used to simulate parts of the Earth system model. They aren't coupled, so they don't typically work together, but what they have in common is the use of this particular mesh, an unstructured centroidal volarinoid tessellation. If you want more information about that and why it's special, there's other slides and other talks about it. But generally, it looks kind of like what you see in the picture on the right, about hexagonal cells, and we can do various different refinements and things that I'll talk about. One of the main focus for the student cluster competition will be the atmosphere cores, and we call that MPAS-A. It's a dynamical solver plus physics parameterization that is used for numerical weather prediction and climate modeling. So dynamical solver means that it models processes that come from equations of motion, particles moving through the atmosphere, wind speeds, and those sorts of things. And other processes like radiation, actions with the land surface, and those things are modeled with lookup tables or some constants. MPAS is freely and widely available in a couple of different repositories for different parts of the work. It was developed as a collaboration between many groups, primarily NCAR and my lab, M-Cubed, and the Los Alamos National Lab and Department of Energy. So this mesh, I decided to show a few more examples of it. On the left, you see a typical about uniform mesh. It usually winds up being hexagonal cells, but we can also do variable resolution of different kinds based on a density function that a user provides. This lets us take large scale information and features of the atmosphere across the globe and see how that impacts and that useful information within a region of interest that we really care about. So like we can put it over North America to get really more accurate cloud dynamics and those sorts of things. We can put it over the equator to study hurricanes and those sorts of things. Or we can even do regional simulations with this as well, like cutting out a section from a parent mesh and adding some extra boundary conditions around that area and simulate that way. As I mentioned, there's other talks and slides or parts of the MPAS-A user's guide that go into more detail about this. For the student cluster competition, what I expect students to do is to be able to get the necessary software libraries and build them, use some sort of version control, typically Git, to potentially change software versions or at least keep track of changes that you make to the code. Use the expect you to use the MPAS build system use GNU Make to build MPAS, and you might have to modify make files for that. Want you to be able to set up a simulation, might have you prepare initial data, copy and link executables and other needed files, modify some of those runtime configurations and IO options, as well as partition these meshes in order to run in parallel. Then, of course, be able to run the simulation on your machine with some settings that you deem appropriate and post-process the results to make my life easier when it comes to grading your results. There may be extra things I add to this for the competition. Did somebody raise a hand or have a question? I can't see Google Meet at this moment.
I'll watch Google Meet for you. If I see any questions, I'll holler, okay?
Cool, thank you. And as I say at the bottom, there may be more or less in this list as I prepare the test cases. Today I'm going to talk about most of these. I'm not going to demonstrate all of it. I'll do certain things like showing, getting the code, building, setting up a run, and a run, but I'm not going to talk about preparing the data since I might not expect you to do that. And I'm not going to spend time setting up the software libraries. I'm going to use some that were pre-built for me in order to keep this flow going. So the software requirements for MPAS are actually pretty light. You just need a working C compiler that conforms to the C99 standard, a working Fortran compiler, which is the primary language of MPAS that works with the 2008 standard, so what some of us call modern Fortran, and an MPI library of your choice. Those are your basis that then you use to build your I/O software libraries. All of our grids, our inputs, our outputs, our meshes are in this netcdf format, which, if I understand correctly, is used by a few atmosphere models, or sorry, other Earth system models as well. Since we're doing an MPI application, we use parallel netcdf mainly for this, and it has a dependence on netcdf libraries. You especially want to look for version 4 or greater, which adds some capabilities for large files that we'll want to use in some of the hard test cases that I will set up for y'all. Depending on what version you choose to use, which I'll talk about why that's important later, you may also need parallel I/O, which is used for, some of the low-level operations. There's an example of this, of a script used to configure and set up your I/O libraries that I give in this link here. One important note, when you start the build, you'll at least need to have the pnetcdf environment variable exported, and maybe PIO as well, to point to where you installed either of those libraries so that during the build it can pick it up and know that you've set things up correctly. Besides these, once we get close to creating a run and you worry about scaling or what you want to do on your system, you'll need this metis tool to partition the meshes, which you might already have the prerequisites for that with the C99 compiler and CMake. So the code can be obtained from GitHub. I expect that any changes that you make will be done in your own fork and not in branches within our main model repository at MPAS-dev, MPAS model. Please do not push branches there. We're a community model and we like collaboration from people, but we don't want to have too many branches in our own model, as that really can bloat things up. In the bottom left in this picture, I kind of give an idea of what the source code looks like. And inside our source directory, there's multiple cores. Many of these we won't have to worry about. It's just the init atmosphere and atmosphere cores that we'll be using for the student cluster competition. These can't be compiled all at the same time, so you'll have to select that when you compile. The figure on the left just gives an idea of how the code is organized once compiled, and that there's a driver that talks to a subdriver that interfaces with the built core module and its routines, as well as the calls that each of those make to the infrastructure. This registry file is something I won't talk about today, but it's within core atmosphere, core land ice. Each of them have a registry.xml file that is used to describe some of the runtime options that go into a name list, some of the I/O options that go into streams, and any variables that can be output by the model. So I go into some detail here about the init atmosphere core, since I'm not going to talk about it a lot today or show it. This core is used to set things up for MPAS, for the atmosphere core. You start with a grid, and then you can go through various stages to add some in time invariant data to create what we call a static file. These are things that we don't expect to change much, things like the terrain heights, land use categories, etc. You then add to that file some meteorological data to create your initial conditions. This can be done with real data, or as I mentioned in the next bullet point, we also have some idealized test cases that we use for debugging or proving that the code works in a way that we think is reasonable. Compiling MPAS uses GNU make, as I mentioned, and typically the command will look like what I show on screen. Make some target, and you need to make sure you have this core equals whichever one you're picking. It's almost always going to be atmosphere for this, and some options that you want at build time. These would be things like debug. If you think that there's a problem in the code, you need to use profilers or those sorts of things. If you want a bit more information, in your executable. Options like the precision of the model that is used for floating point numbers. This can be double or single, and a couple of others. So this is my reminder to switch over here to a terminal. I want to just demonstrate real quick how to get the code, a little bit of what it looks like on the terminal, and start a build before I get to a couple of other things. So I'm just going to get the model from GitHub. And I want to show the make file real quick. Oh no. Okay, that window does not want to work with me right now. Good thing I had a backup. So what I want to show here is these targets. They're all given at the top of the make file, and they're generally corresponding to compilers or compiler suites that we expect that you might want to build with, and their compiler flags. This top level make file might be something that you have to modify for your build set, your hardware, for whatever cluster setup you're running on, whatever compilers you think are good. You'll need to define like your optimization options, debug flags, and some other options that are important for the compiler to make sure that it works. I want to switch back here, and I'm using NCAR's derecho system, a HPC that we have, and I just want to point out that I've got Intel as my compiler, some Cray MPI, and you can see some of the libraries that are important for I/O are already loaded for me. So I'm going to just start a build for Intel with the Atmosphere core, and in the interest of time, I'm also going to speed that up a little bit. It's going to output a lot of text, some of which is important and you might want to save in a different file, but you can see all of the options that are being used and how these are being interpreted and the progress as it builds. I'm going to leave that to go in the background. So some of this I've already said, and some of these slides I'm going to skip, but some important things to point out is, again, you might be expected to modify or add your own targets to this top level make file. Each build that you do is in place. We currently don't have a way, like with CMake or some other build systems, to build in some other directory. This means that in between building cores, like the init atmosphere core or the atmosphere core, since the infrastructure is shared, you need to clean in between using this make clean with a specified core command. This will clean the infrastructure and get rid of any executables that exist associated just with that core. So like if I make the init atmosphere core and then clean just the atmosphere core, my executable for the init atmosphere will stay, but all of the module and .o files deep in the source code will get deleted and rebuilt to make sure that we create the correct executable for whichever core we specify. But this also means that if you want that different versions of the atmosphere core, for example, you need to copy it, rename it, or do something with it before cleaning it, or you'll lose it and just have to repeat things. One other important thing, if you are trying to run without internet access on your cluster during the competition, you'll need to look at the build system a little bit and find a file that is used to check out the lookup tables for our physics routines. One of the first steps in the build process, if they aren't already there, is to fetch them from a different Git repo. They're version specific as well, so if you're changing branches, you might need different versions of these files as well. And just a note about MPAS being built in double precision by default. You can use single precision to cut down on simulation time and output sizes. But if file sizes are the only thing you care about, you can actually run the model in one precision, say double, so that you get very accurate simulation, but you can output in single precision so that you cut down on size and can make post-processing a little bit quicker. I'll explain how to do that once I talk about the streams file. Is this? No, not quite finished building yet. So I give an example of what this will look like at the end. And the important thing to point out is the model, the executable will exist there, as well as some of these extra files on the right are what's used to control runtime options. All of these other files that you see kind of in light blue or ending in tbl.dbl, those are the physics lookup tables. All of these that I've pointed out, the executable, the name list, the streams, stream list, and these .tbl and .dbl files need to be in your run directory. You could run just in your MPAS model directory, but I find that that gets rather cluttered over time. So I will typically copy these files, the executable, the nameless streams, lookup files to some other run directory and get that set up there. Let me show what one of those run directories looks like. This is one that I prepared beforehand and is one of our benchmark test cases that we use. Just to make sure that the model works as expected and for convenient start on some other thing on whatever hardware you are starting with. I'll show in a little bit how where you can download these things from or how you can set these up on your own. You'll at least need your input data file to be present, as well as these other files that you have copied over. The important one to show first is our nameless.atmosphere. This controls a lot of our runtime options. It has MPAS is a research model, so it has a lot of ways to tune and to change the way the simulation is run. So that's where there's things like the integration order and all of these parameters that I usually don't touch, like the advection order, whether we do positive definite or monotonic, transport modeling, and those sorts of things. These have default values in the code, so it makes almost no difference for what we will be doing for the student cluster competition if we just delete a lot of these. to start with and narrow it down to what I consider important. Which I do real quick. Since these have default values, this causes no problems. The config DT sets up our time step, basically what is done in the model. And this needs to be specific to whatever resolution you're setting up. You'll want to make sure to match your start time with whatever is in your initial conditions and set up the run, which I'll tell you what to do for that, but set it up to go for as long as we need to create the results that we want to post-process. This is another config len display is another, it's a bit of a bugbear for me. It is something that is used, is something that is mesh specific. So if you change the resolution that you're running with, you need to make sure to match this to what you're using. I think I've maybe said about enough on that. So I give some more guidance on this in the slide about this. One really important thing to note is that for model stability, the time step that we set should always be 6 times the cell size of whatever mesh you're using in kilometers. So for this setup that I'm showing on the right, we're using a mesh that is 120 kilometers in size. So the time step winds up being 720 seconds. If we change to like a 3-kilometer mesh, then it needs to be 18 seconds. If this isn't set correctly, it can cause just completely unrealistic results and potentially a seg fault in the code, though I have just trusted the scientists and other recommendations to stay within this realm. If you want, again, extra information about these, that's in the user's guide. And you can also look in a registry file or send me a message to get some more info. The input and output from the model is handled by the stream, what we call streams in MPAS. These are written in the streams.atmosphere file. It's very configurable, and you can have user-defined streams as well as some that are special and important to the model, such as input, and restart files. User-defined streams can be things like that we call history, which is used to output things like precipitation, wind speeds, I think even precipitation types and other things. They have certain streams have certain characteristics that are important, and the ones that I really want to point out are the intervals, input and output intervals, that can be adjusted so that you aren't spending all of the model time reading or writing to files. You also might want to adjust the IO type. If we are running on a really, really small mesh or small in cell size mesh, meaning that there's many, many cells in the simulation in general, you'll need to set the IO type to this PNet CDF, CDF5 type. That just means to use some of the large file format operations to make sure that the files can actually be interpreted after being written. And as I mentioned, you can also set precision in these to double or single, so that at runtime, even if the model is compiled a certain way, the files will be written in the precision that you want. So as I showed a little bit with the run directory, looks a little bit like this: your executable, physics lookup tables, your initial file, nameless, streamless, and what I want to talk about next are these graph partition files. The graph.info, the init.nc contains all of the mesh information, the cell sizes, the edges, and those sorts of things, as well as the meteorological data. The graph.info talks about how those cells are connected to each other and which cells are neighbors to each other. That is then used by MPAS or some other tools in order to create our partition files. So as I mentioned, is run in parallel by decomposing the mesh across ranks and creating somewhat of a picture that looks like this. We can, excuse me, using MPAS, we can set up the number of partitions for whatever simulation we think, or whatever number of ranks we think is appropriate for a simulation. We could just divide up the globe into 4 sections, into 36, or whatever. MPAS tries to keep the number of cells in a partition about equal, so that there's an equal amount of work, while minimizing the size of the edges of those partitions so that we don't spend a lot of time in the model just communicating with neighbors to keep the simulation results realistic. And another reminder to switch over. So here,
Dylan,
yes.
quick, do you want to wait till the end for questions, or you want to take them as they come in?
I could take one now.
So we have a question really quick, which is how much storage do we need to run MPAS for SCC? And do we need a parallel file system?
Let me start with the second question first. Generally, yes, a parallel file system goes a long way to model performance for this. Since we're using PNet CDF and or PIO, you'll want that so that the model doesn't spend like 50 seconds writing files and only 1 second in the actual simulation for the time step. The size, I'm not fully confident to say for sure. Expect maybe, I think I would have to get back to you on that. It will be on the order of a few tens of gigabytes for the type of simulations that I expect.
All right, thank you.
Yeah. So right here, I'm just going to take, where's my cursor, please? Our graph info and generate a partition real quick for so I'm going to do a couple of different ones. This runs really quickly. I just want a couple of different ones to get an idea of the simulation time taken on this mesh. This is a mesh with 4,000 or 40,962 cells. This corresponds to about a 1 degree latitude longitude resolution as used in other models. And the cell sizes are about 120 kilometers apart. Going to copy over the atmosphere model that was built here. And starting a simulation is fairly simple. You just need to use your MPI exec or equivalent command to start it, specify your number of ranks, and point that at the atmosphere model. This doesn't output, Well, that is interesting and not what I meant to show in this talk. Nothing like errors in a live demo.
That's okay, Dylan. When they experience this, then they'll know what's going on, right? So
Yeah.
it's all good.
What I hoped to show was the model time stepping and looking at this log.atmosphere.out file. Instead of outputting things just in the moment to standard output or standard error, the MPAS model sends that to log.atmosphere.rank number in either .out or error. Hopefully, if everything goes right, there isn't a .error file. In this case, because of the way it failed, there actually isn't even one. But in order to get a sense of how the model is running and what's being done, you would look at the log.atmosphere.out of some kind. It has a long preamble about what was done to set up the run, what variables were read from the name list or the stream list. And if this was running correctly, it would be talking about the amount of time taken for a time step and some idea of the wind speeds that are happening in the model to see if the simulation is kind of going off track. Hopefully the wind speeds in the horizontal and vertical direction stay realistic, a few meters per second vertical or around 80 meters per second in the horizontal. So I talked about some of this already, how to start the run and these expected output files. If the model had run successfully, what I look for to, as just kind of a quick check of, oh, did it complete, is this timing table at the bottom, which is contains a fair bit of information, but it won't be printed if the model didn't succeed in some way. I'd hope to spend a little bit more time with the simulation, but unfortunately that might not be working for me today. So once that model run succeeds, we'll have a few output netcdf files ending in .nc, and those can be interpreted either using Python scripts or NCAR command language scripts to create visualizations. I'll provide the ones that I think are important for the student cluster competition. But if you're using this on your own and want to look at some of the output later, sometimes it's easiest to convert them to latitude, longitude grids so that you can use tools like NCView or some image production scripts that are used in other models so that you can compare, say, the weather research forecasting model, WRF, or forecast by NCEP or IBM's weather company to the results given by MPAS. We have a special tool called Convert MPAS, which does it, which is also written in Fortran. And I'm really not happy about my simulation, so I might help show a little bit of that later. One special note and something that I spend a lot of my time working and fighting with is MPAS Atmosphere with OpenACC porting. About 2017, there was some work done on this to use NVIDIA GPUs and split the simulation between dynamics on the GPUs to really speed that up and get better throughput, and keeping some physics schemes on the CPU in a setup that we call lagged radiation. This work was carried out by NCAR, NVIDIA, and students at the University of Wyoming for the weather company. It's in production, as part of the GRAPH, the Global High Resolution Atmospheric Forecasting System, since 2019. But it's maintained in separate branches for the moment because this lagged radiation and some other things make it more complicated to run. And there's also been code divergence over time. If you think it's going to be useful for student cluster competition, if you think it's going to be something you want to try, you'll want to make sure to use these branches and know that some features are going to be missing. If I expect regional simulations especially, you won't be able to use the OpenACC versions for this, and you might find some pernicious bugs that happen if it's not set up for the exact physics schemes or radiation intervals that are expected.
All right, so we have a question on that.
Yes.
The OpenACC version, is it for NVIDIA only? Will it work with AMD or Intel GPUs?
If you have a compiler that can work for that hardware and understands OpenACC, then I would say maybe. These particular branches were developed on a specific IBM server setup that is similar to Summit's HPC system. Or our Oak Ridge National Labs Summit system, which uses V100 GPUs. We've been able to get some work on NCAR's derecho system, which uses A100s, but we're having to fight against some parts of the code right now in order to get some results at high resolution. Here is a slide I'm providing to point to some other information, the GitHub repo. This MPAS-dev.github.io is where you can find the user's guide, link to the tutorial, as well as downloads for a lot of the meshes. Some of these talks in the tutorial go into more detail about the mesh, mathematics, physics schemes, the init atmosphere core, which I didn't cover, and others. I think Jeanette should have a link to the overall forum that we want to use for the cluster competition. But if there's some problem that you encounter that you think might have been answered before, I give a link to the WRF MPAS forum, just something to Google around on. Or if for some reason you feel like you aren't getting questions answered in another way, you might be able to get more interaction with others of my colleagues through this forum. Though again, we don't want things to go through there first. And this is just a supplemental slide that I'm providing just for some information after the seminar. I'm going to try to find a successful run of MPAS real quick so I can talk a little bit more about the expected outputs. Okay, there we go. So this is a previous run that I did. And the important things to point out here are the existence of these restart files. Sorry. These are generated according to the rules that we set up in the streams.atmosphere. And you can control the intervals that they're created using these variables here. These are probably going to be the files that I will care about the most for the cluster competition, since they are our most complete model state that we get out of it, and will be what I use to check that the simulation completed, that was realistic, and that the outputs that are generated can be used to actually restart a model and run to completion on some, over a short time scale. The log.atmosphere parts that I wanted to point out earlier. Once the run gets going, you'll see messages about the time step beginning and start getting some idea of the wind speeds that I mentioned, as well as how long it is taking to complete each time step. We'll go and can be very verbose, talks a lot at you in these files. That's why we don't output to standard out. And once everything finishes, you'll see a nice message about the run finishing, as well as this table that I mentioned. I think I went through a bit of my information quicker than I thought I would. So if there's any other questions or things that you would like me to show, would like to open the floor back up to everybody.
Yeah, here's another question that just came in. Are there some input files that we can download to test performance with the latest version of MPAS? There are some input files for MPAS 7.x, but they do not work with version 8.
It's in my understanding, we should be backwards compatible with a lot of things. So I'm curious what issues you're seeing besides what I just experienced, which was with the physics lookup tables. Those, like I said, are version specific, pulling from another repo. So there can be IO issues there. I'd be interested to know what exact error it was that you were seeing.
Does the poster want to speak up or not? That's fine too. But what you're saying, Dylan, is that the input files for MPAS 7 should work with MPAS 8.
Yes, as long as you've linked the correct physics tables, just the init.nc should be applicable.
So you're saying there are probably more issues with the physics tables than there are with the input files, is what you're saying. Yeah.
Yeah.
So that may be what you've run into, Sheng Long. Maybe it's a physics table problem. Are there any other questions?
I guess before we switch over to that.
Yeah, that's what Sheng Long says. It's with the TBL file. So that would be those physics tables.
Okay, yeah.
That's the problem, yes.
Let me.
Yeah, you've got some time if you want to troubleshoot this, right? Take a little time and see if you could work this out. Again, this is all good stuff. Shows them what to do when they run into trouble, right?
So yeah, as it said that there was an IO syntax error for me. So what I did was copy one of the benchmark directories for version 7. So there was the IO error that I should have expected, and I can just grab all of these files and copy them over. Okay, that is taking much longer to fail. There we go.
So just to make sure I understand, so you grabbed the right physics tables from, was it just the root of the correct model? The
Yeah.
correct Git repo that you pulled down. That's where you copied these from, right? You said make sure you had the right ones.
Right. So on a successful build, there will be links to these given in the top level of the MPAS model. If for some reason it fails or you just need those tables, you can look in source, core atmosphere, physics, and physics wharf/files. That's where all of these get downloaded into. And so since I have a minute, let me show this. Checkout data files is what's used to fetch the to match the MPAS version with the expected version of the lookup tables. We look for whatever version is in our model and then fetch the corresponding branch from the other repo and toss those files into physics wharf/files. That's the area that will be checked each time a build is run. So if you don't want internet access on your cluster, you might have to switch some of these files out in between builds.
So how's your build going? How's your run going now?
Thank you. Apologies if anybody hears a giant train going by. It is going pretty well, although you can see that this is taking about 8 seconds per time step. And that's because I chose just a really low number of ranks for this to really demonstrate how important it can be to fine tune that for the mesh size, your hardware, or what you're setting up. 8 seconds is kind of long for such a small mesh. So I'm actually going to abandon this run real quick. And since I generated another partition, well, let me demonstrate what happens if we just aren't set, if we skip the mesh partition step and just try to run greedily. If we're trying to say run on 18 ranks and generate an error real quick, we'll get our .error file, which hopefully will be more helpful than this giant mess as output there. It tells us that we requested for 18 blocks, but it's not able to find that. So I can use GPMetis to generate that. And run again. In the run directory, it will just overwrite any of the existing output files or standard out, standard error files as it encounters or needs to write to them. So those are another thing that if you're running multiple runs in the same directory, you might want to save some of those files before you start another run. And here, it's better, 4 seconds. I think this can still go even faster. Let me try with 36. After a while, of course, this tails off due to communication, just not having quite enough work and those sorts of things. Let's tail you. So it's better. Typically, I look for this to be about under a second, maybe about a half a second per time step. So try and play around with different partitions and different number of ranks for your system.
All right, does anybody else have any other questions? Give people a minute here, a few seconds to. All right, so we'll make this recording available in the slides, still in slides. We'll put that up on the SCC website here, in the next day or two. So, keep an eye out for that. And thanks a lot, Dylan, for doing this. That was really lovely. I learned about MPAS-A, so that's good. So if there's no other questions, I think we'll go ahead and call it quits. But yeah, do you have anything else?
Let me point y'all to one other resource that I mentioned in the slides, but I used a lot when I was learning this, even though I wasn't present for these. This tutorial was given in Boulder in 2019 and points to a lot of these PowerPoints that my coworker Michael prepared that go into in-depth detail, as well as if you scroll down, there's almost a bit more of a conversational guide through a lot of these steps in compiling, in creating initial conditions if you need, in setting up a run. It should be a repeat of this information, but of course, people learn different ways. Please use whatever resources work best for you.
Did you have a link to this in your slides?
Yes. And if anybody wants to grab it today, I'll put it in the meet chat here.
All right, anything else you have, Dylan?
I think I'm good.
All right. Then I think if there's no other questions, we'll just thank Dylan. Thank you so much. It was really lovely. And we will see you all at the next webinar, which will be in a couple weeks. We'll get out some information about that. I will also say that we're working on getting the discourse server up, which is the chat server we'll use for asking questions of the judges. So we should get that up in the next day or two. So we'll get you on that so you can ask Dylan questions directly through the discourse server that we're setting up. Okay. All right. All right. Well, thank you. And we'll see you at the next webinar. Stop this recording.